Welcome everybody to week 4 of Engineering, Mathematics and Modeling, where we will be talking about systems of linear equations. And I will start with a first example of a system of two equations of two variables. So x plus y equals 2, 2x plus 3y equals 5. And we want to find a solution that satisfies both these equations at the same time. Now, a system of linear equations can be as long as you want and have as many variables as you want. And they are expressed in the number of unknowns, or the number of variables, and the number of equations. So here we have two unknowns, two variables, and two equations. Now this is typically solved if it's such a small system by the method of substitution. But before we go into solving this, I want to give you a representation of what we're really looking for. So any equation like this can be rewritten as a line. So the first one is the line y is equal to 2 minus x. And the second one is equal to y is equal to 5 minus 2x over 3. Or slightly more easily written, 5 over 3 minus 2 over 3x. And these two lines can be visualized. So the first line, y is 2 minus x. That's an easy one, 1, 2, 1, 2, and that is this line. And the other line, minus 2 over 3 times x plus 5 over 3, goes a little bit like this. And you see that there is an intersection point here. With the solving of this set of equations is the same thing as finding points, the combinations of x and y. So this is the point 1, 1, that satisfy both equations, and they lie on the intersection between these two lines. So if we find the intersection of these two lines, we also find the solution to our set of equations. So this gives us a visual representation of what we're doing, which is very easy to do for two variables and, well, any number of equations. I am, though, going to write this system of equations slightly differently. This won't be absolutely necessary for now, but is an introduction for something later. What I want to do is remove the letters x and y from the notation and rewrite it differently. So if we have these two equations, 2x plus 3y is equal to 5, and the first one, we will write that in a kind of matrix form as, well, we have 1x plus 1y is equal to 2, and 2x plus 3y is equal to 5. And we write this, and this is called the augmented matrix of this set of equations. Now, this is something we'll use later for larger systems of equations. I just wanted to introduce it here. Now, a 2x2 system here we typically solve using the method of substitution, where we take one of these equations, let's say x plus y equals 5, and we say that then we know that y is equal to 2 minus x. This y gets substituted for this y here. So this is the first equation, just rewritten. When we get 2x plus 3 times 2 minus x is equal to 5. And this eliminates y from the second equation. We are left with one equation with only one variable, and that can be solved. So here we have 2x minus 3x, so minus x plus 6 is equal to 5. And if we shift the 5 to the left, the x to the other side, we find x is equal to 1. And once we found x is equal to 1, we can find our y, which is 2 minus 1 is equal to 1. So we find x is 1 and y is 1. So the point x comma y is equal to 1 comma 1 is our solution. And it is the only solution, but that could have already been seen from this diagram, because the intersection of these two lines only has one intersection point. Now, could we have done this in a different way using what we know from matrices and their inverse? Well, yes. Let's rewrite this system in the form that it is no longer a set of equations, but it is a matrix equation. Let's take the matrix A is equal to 1, 1, 2, 3. Let's take the vector x to be x, y. And let's take the vector b to be 2, 5. Now these two vectors in this matrix can be used to write out A times x is equal to b. So a matrix times a vector is equal to another vector. Well, we know that because A is a 2 by 2 matrix and x is a 2 by 1 vector, that if we multiply A by x, we get a 2 by 1 vector. But instead of having a known vector, this x is now equal to the unknown. Now, so this system of equations can be written as a matrix equation, and we can see that it works because if I take A times this vector, I get, well, let's write it just in a corner here, 2, 3. So this is my way of writing out matrix multiplication. I get 1 times x plus 1 times y, so that is x plus y, 2 times x plus 3 times y, 2x plus 3y. So this is the result of ax is ax times b, so we get x plus y, 2x plus 3y. This vector is equal to the vector 2, 5. And we see we have an equality of two vectors, which means the first coordinate must be equal to the first coordinate of this vector must be equal to the first coordinate of the second vector. So we get x plus y is equal to 2, and we get 2x plus 3y is equal to 5. So it's the same problem, the same set of equations. But I want to solve this differently. I want to stay in the realm of matrices. So what I want to do is the following. Let's say we have the inverse of A. Well, the inverse of A times A is equal to the identity matrix, and in this case it will be the 2 by 2 identity matrix. Let's take this equation and on both sides of the equation multiply with the inverse of A. And as we do this on both sides, it is valid. Now, the inverse of A is something we can calculate because we know that the determinant of A is equal to 1 times 3 minus 1 times 2 is equal to 1, and that makes it easy to write out the inverse of A. So this is, well, calculating an inverse of a 2 by 2 matrix, which we did last week. But now I get this. I know that A inverse times A is equal to the identity matrix, and this is A inverse times B, where B is of course a vector. Now what is the identity matrix times X? So the identity matrix times X is 1, 0, 0, 1 times X, Y. Well, if we multiply this out, this is X, y, it's the vector itself. Multiplying the identity matrix, well in this case the 2 by 2 identity matrix by x, is the same as the vector itself. So what we have here is that x is equal to A inverse B. By using the inverse of the matrix, we have found what we are looking for, which is x. Remember, we were looking for combinations of x and y which satisfy this set of equations, or points that are on the intersection of this line. So we are looking for our vector x. This is our unknown. And now by using the inverse of the matrix, we have an expression that x is equal to the inverse of A times B, but that is something we can calculate. If this is our inverse, then the inverse times B is equal to 3 minus 1 minus 2, 1 times our vector B, which is 2, 5. Well, A inverse is a 2 by 2 matrix, B is a 2 by 1 vector, so this multiplication is easy to do. Its first coordinate is 3 times 2 plus minus 1 times 5, which is equal to 1. And here we get 2 times minus 2 plus 1 times 5 is equal to 1. And we find that this is equal to 1, 1, which is the exact same solution we found here and by substitution. So we can use the inverse of a matrix to solve a system of linear equations by rewriting this set of equations as a and I'll use a different color. We can write this set of equations as a matrix multiplication, which we can solve by using the inverse of the matrix. So in the next video, well, in the next part, I will continue with another example, but the main part of this introduction is that we will be looking at systems of linear equations, which we want to find the solution xy which satisfies both of these equations. We have a visual representation which will be important in the next part. We can write this system as a multiplication of a matrix and a vector which is equal to a vector, so this form here. And I'll write it out here, is that this system of equation is equal to 1, 1, 2, 3 times x, y is equal to 2, 5. So this is this equation here, where we have three ingredients. This is our matrix A, this is our vector x, and this is our vector b. And by taking the inverse, we have an expression for our unknown and a way of directly calculating using the inverse of A.